In the previous segment, we looked at how we could follow a graphical approach for determining V1 bar and V2 bar. In this video, we're going to look at how we could do it using an analytical method. So if we were given some sort of mathematical model to describe delta V mix. Okay? All right, and so for this example, what we're going to consider is, let's take a look at this mixture between methyl formate and ethanol. So it forms this curve right here. Okay? And so we see we have this parabolic curve. And so based on the shape of this curve, so this is, we're looking at an analytical method. And essentially, the analytical method means you're just going to describe your delta M mix using an equation. Okay? Alright, and so for this example, for methyl formate, I think it's just and ethanol, we have this sort of mixture, forms a parabolic curve like this. And so, let's say it's been proposed, or that we're going to propose, that our delta V mix, our molar delta V mix, is going to be equal to A x1 times 1 minus x1, right? And so that we would have some sort of like A x1 minus A x1 squared equation, okay? And so that's why our parabola is upside down, okay, because we have a minus x1 squared here. Okay, so we're going to propose that the delta V mix, to describe this upside down parabola, follows this model, okay? And so if we take a look at the figure again, so from figure, we see that delta V mix at 0.5 corresponds to a value of about 0.2. From figure, delta V mix at x1 is equal to 0.5 is equal to 0.2 centimeter cubed per mole, which from our model would mean this. So A times 0.5 times 1 minus 0.5, which is also 0.5. So we have all those values. Our only unknown is A. Therefore, we estimate that our A parameter is 0.8 centimeter cubed per mole. Okay? And so we have this model to describe delta V mix, and we even figured out what A was from the plot. And so let's say that in general we're given V1 and V2 squiggly. If we had those values, can we figure out a way to derive a model to allow us to get V1 bar and V2 bar? Okay? Alright, and so let's go through the approach of how one would do this. And so we know that our total volume of the mixture is going to be a sum of the molar volume of the ideal solution plus our delta V mix, right? So this delta V mix captures the non-ideal behavior of the mixture, okay? All right, and N, of course, is the total moles in the mixture. For the ideal solution, we know it follows this form, pure as 1 minus x1 V2 pure. And then delta V mix, that's going to follow that model we proposed up top here. A x1, 1 minus x1. Alright. We can multiply across the n here into all of the mole fractions. So V is now going to be equal to N1 V1 tilde plus N2 V2 tilde plus A N1. And since we only had one of these moles, I'm going to multiply by the x1 here. But for this x2 here, I could also describe it in terms of moles as well. So N2 N1 plus N2. Right, since that's the definition of a mole fraction. Okay, so here's, just an equation based on our model for delta V mix. We can now write an equation for the total volume. To figure out V1 bar and V2 bar, let's apply their basic definitions. For V1 bar, we know that it's the partial derivative of V with respect to N1 at constant N2. So we just need to take the partial derivative of this equation with respect to N1. First term, the derivative is just V1. There's no N1 here, so that term just goes away. Here we have an N1 in both the numerator and the denominator. So we have to apply the quotient rule, or split it up and apply two product rules. In any case, we get something that looks like this. N1 plus N2 squared. Okay. All right. And essentially what we have here is we have N2 over total N. That is just a mole fraction. And here, since this part's squared, we also have like N1 over total N and N2 over total N. So we could rewrite those in terms of mole fractions again. So A x2 minus A x1 x2. And so if we factor out the A, what we get is V1 squiggly plus A x2 1 minus x1, which by itself is x2. Okay? So now we have A1 x2 squared. So our molar volume for species 1 from our model derivation can be described by this. And similarly, if we went through the same exercise for V bar 2, we would find that V bar 2 would follow this relationship. Okay. Right, and so at least, the way we derive the model, it is somewhat simple and kind of makes intuitive sense, right? Basically, the partial molar quantity, or the partial molar volume for species 1, all we're saying is that it's going to be equal to the pure molar volume of species 1 plus some non-ideality term, which changes that value and adds to it. And the same with V2 as well. Okay, and we could see that these are both positive, and so the effective volumes of each of these species are going to be larger than the pure species, and so that would lead to a volume that's larger than one would expect. Okay, that's essentially what these equations are describing. Okay, and so nevertheless, though, these equations are very simple, and they do seem to describe the data. But what we need to check is that these equations are thermodynamically consistent. Okay, I have a lot of room. All right, and so now that we got these equations for V1 and V2, we need to make sure that they make thermodynamic sense. So let's check that V1 and V2 equations are thermodynamically consistent. And so we're going to do three things to make sure they're thermodynamically consistent, and the models need to pass all three tests. So the first thing we're going to check is the value of these models at their limits of the mole fractions. Okay? And so for V1 bar, let's take a look at the case where we have a pure species of species 1. So x1 is equal to 1. And conversely, that would mean that x2 is equal to 0. Right? So v1 bar is equal to v1 squiggly plus a times x2 squared. If x2 is at the limit of 0, that means we get back v1 squiggly. So that is what we would expect. And similarly, we take the limit of v2 bar as x2 goes to 1, and which also means x1 goes to 0, we would have a times 0 squared, and we would get back the pure v2. Okay, so the models pass that first check. The next thing is we need to check the additivity. Right? Such that the molar volume of the entire mixture needs to be equal to the sum of xi vi hat. Right? Okay? Alright, and because that's, if we go back here, we had in it, oh, actually, where do we have it? If we took this volume and divided it by n, we should expect to get back this equation. Okay. Alright. Okay, so to check this, let's just apply the definition. Xi vi bar I equals 1c. And so x1 v1 bar plus x2 v2 bar. And so we know what, from our model, v1 is equal to this, and v2 is equal to this. We could distribute across various factors. Alright, and so this x1 and x2, the sum of those two things we know, since there's only two components, we know that sum should equal 1. And so what we get back is that V molar is just equal to x1 v1 plus x2 v2, which is plus a x1 x2. So after we add in both of our models, we get this equation, which matches exactly what we got here. Okay? Where this 1 minus x1, those are just x2s. Okay? And so our models pass the additivity check. So two things looking good. Then the last thing we need to check is now, do our models pass the Gibbs-Duhem at constant temperature and pressure check? Okay, and so if you remember, when I talked about Gibbs-Duhem earlier, essentially this is what we would be looking for. That if we took our models, took the derivative of them, and multiplied them by the mole fraction, if we added up those sums, all those things would equal to 0. Okay. All right, and so from Gibbs-Duhem, it's telling us that x1, and if we took Here it's just like a total derivative, but essentially if we divide it by some variable like x1 or xi, the Gibbs-Duhem should still apply. Okay, so what we're going to do here is we're going to have x1 times the partial derivative of v1 bar dx1 plus x2 dv2 bar over dx2. Let's now actually take the partial derivatives of each of the models. So d dx1 v1 hat plus a 1 minus x1 squared plus x2 d dx2 v2 plus a 1 minus x2 squared. If we work out that math, we get that it's equal to x1 minus 2a x2 plus x2 2a x1. Multiply those across and we get negative 2a x1 x2 plus positive 2a x1 x2. Same magnitude, opposite signs, those equal to 0. Okay? And so this tells us that the model that we proposed for delta V mixing not only passes the Gibbs-Duhem test, it also passes the check for additivity and also satisfies the limits that we do expect for the pure species. And so now, because we passed these 3 different tests, this means, or what this suggests to us, is that our delta V mixing model is thermodynamically consistent. And there's at least reasonable chance that this model can accurately describe the thermodynamics of the mixture.